Last unit of the year, and also one of my favorites, topic 11 is all about three-dimensional shapes, particularly the ideas that we can use to turn a two-dimensional shape into a three-dimensional shape, and also volume of the various different types of three-dimensional shapes. So section 11.1 is what we're going to do today. That is the one that's going to make this good connection between the two-dimensional shapes that we've been using for the rest of the year and our 3D shapes. We've got a few vocab words here. We're kind of going to jump around as we go. The first vocab word we need to have here is a polyhedron. So you know how a polygon is a shape that's two-dimensional and it has straight line sides? A polyhedron is a three-dimensional version of that. And in fact, this prefix or this suffix hedron is going to be on a lot of our 3D shapes. So a 3D 20-sided shape is an icosahedron. A 3D 8-sided shape is an octahedron instead of like an octagon for a two-dimensional shape. So here we're going to say a polyhedron is a 3D shape with polygonal or polygonal, that's the way we write the adjective form. So it just means polygon, faces. So all of our faces they're flat. And that's the important part of a polyhedron is all the faces are flat, they've got straight line edges. So for example, a sphere is not a polyhedron because it does not have flat faces. Today we're mostly talking about our polyhedrons. So when we come down here, we'll come back up later. We're gonna start by making a rule about our faces, edges, and vertices of different kinds of polyhedrons because there's a relationship here between the number of faces that a shape has, the number of vertices that it has, and the number of edges that it has. This relationship was discovered by a mathematician. His name is pronounced Euler, and he was a really interesting guy. He did a lot of stuff in math, particularly for algebra, but he also did some stuff in geometry, and this is one of those things. So the first thing we want to do is we want to count for each of these three-dimensional shapes, each of these polyhedrons, the number of faces, vertices, and edges. So this triangular prism has 5 faces. The vertices would be the corners of the shape. It's got 6 of them. And then the edges are, of course, the lines where the two faces meet each other. There are 9 of them. And we're going to continue to do this for the rest of these shapes. If you want to here, you can pause the video and count out and write down the number of faces, vertices, and edges. But here are the numbers we should have. And then our 6-sided, this is actually a hexagonal prism, but it's not a regular hexagon like we're used to seeing. It's got to be 8, 12, and 18. So what Euler did is he said, I think that there's a pattern here. When we go up one face, some other things are always going to happen. When we go up one face, we go up 2 vertices, and we go up 3 edges. And that pattern continues every time. He says, how can I turn that into a formula? So he came up with this formula that relates these 4 values. We use F plus V, the number of faces plus the number of vertices, is going to be equal to the number of edges plus 2. And that's what he got after he sort of consolidated and condensed all of the patterns that he had been seeing amongst these shapes. So this is what we call Euler's formula. We'll put it up here in the Euler's formula box as well. I'm going to write it in words. Faces plus vertices. Vertices equals edges plus 2. So we can go ahead and use that in some of our 3D shape questions. So first here, we have polyhedron-shaped game pieces, or a 20-sided dice. If you're somebody who plays a lot of board games, you might have used 20-sided dice before. And Juanita is entering the number of faces, edges, and vertices that she wants her shape to have into a 3D printer. If she wants her game piece to have 20 faces and 30 edges, how many vertices does the place have? You might be able to pick up on the fact that this is just an easy plug and chug problem, right? Our Euler's formula, F plus V equals E plus 2, means that we're going to put in 20 faces, plus we don't know how many vertices, equals 30 edges plus 2. So there, 30 plus 2 is 32, equals 20 plus V. And if we subtract 20 from each side, we can easily find out that V equals 12. So the number of vertices that this shape has is 12. The next thing that can happen is we can use Euler's formula to decide whether we have a polyhedron or not. There are some combinations of faces, edges, and vertices that don't make a polyhedron because they don't come together at all of the right spots. So here we can plug in 4 faces, 5 vertices. We can see if that is equal to 8 edges plus 2. Well, 9 is not equal to 10, so we cannot have this polyhedron. There's not one that exists in reality. So no, it does not work in Euler's formula. So those are what we're going to look at as far as the relationship between the faces, edges, and vertices of a 3-dimensional shape. The other stuff we're going to do today is mostly about cross-sections and what I would consider to be the opposite of a cross-section. So what is a cross-section? Well, this is where I have put the Fruit Ninja logo on the concept box. I don't know how much longer I'm going to be able to do that and have it be culturally relevant and have you guys know what it is. But that is the Fruit Ninja logo, and of course, that is the game where you toss fruit up in the air and then you've got this sword or katana thing you use to slice the fruit. And it's a really good demonstration of the idea of a cross-section. Because when we have a cross-section, we're taking a 3-dimensional shape and we're slicing it somewhere. And we're looking at the shape of the face we create by that slice. So if we were thinking about what does the cross-section of this watermelon look like, of course we would say, well, it's going to be a circle. That's going to be a circular cross-section. Let's see how accurate of a watermelon I can draw here. Probably not that great. And then we've got all of our interior and our seeds. So our watermelon cross-section would be a circle. But if you think about it, I could have made a different cross-section of this watermelon had I sliced through it this way. Because if I sliced through it in that direction, I would have made an oval cross-section. It would be taller and wider instead of being a circle with the direction that I cut through in the picture, or I guess that the logo cuts through. The actual definition of a cross-section is going to be the intersection of a solid and a plane. The intersection of a solid and a plane. And the reason we use the word solid here instead of polyhedron is because the word polyhedron excludes some of our 3-dimensional shapes. The round ones, cylinders, cones, spheres, they're not polyhedrons, but they are what we call a solid, a 3-dimensional shape. So any of our 3-dimensional shapes are considered a solid, right? And of course, the plane, in the case of Fruit Ninja, would be the sword. It's the slicing apparatus here. So these can be a little bit difficult to imagine. Actually, I'll talk about this now. Cross-sections are hard to visualize for some of us, especially if just general 3-dimensional shapes can be hard to visualize. So what you can do for help here is you can go into Schoology, and there is a really nice assortment in Schoology of resources here. If you go into the Topic 11 folder and you hit Cross-Section Simulations, you come to this website, you can scroll down a little and you'll find all of these different types of shapes that we can use. So for example, if I hit sections of triangular prisms, I get this, this tool, this interactive tool that I can use, and I can change things around here. I can rotate the shape, and I can say, okay, I can make a triangle cross-section in this shape, but what if I rotate the plane some more? Hey, look, now my cross-section has 4 sides, and I can rotate it around and look at what that looks like. And I can think about, well, I wonder if I could make a cross-section with 5 sides or 6 sides. I don't know. But I can rotate this around. Oh, that one seems to have 1, 2, 3, 4, 5 sides. So there is a way that I could slice through this triangular prism and make a pentagon shape, right? So these are really fun to play around with. I encourage you to do this. Usually when I'm teaching in person, I have students play around with these tools for around 5 minutes. So if you're able to do that, that can be really helpful to you from a visualizing perspective. And then we can go back into our notes. We can work on some cross-section problems, right? So here I have a pyramid, and it appears to be a pentagon pyramid because the base is a pentagon. And we want to know the cross-section shape. So where this blue plane intersects the pentagonal prism, we've got a pentagon-shaped cross-section. So when it says what is the shape of the cross-section, we'll just write a pentagon. But then we also have to do some imagining because sometimes we won't have such a specifically clear drawn picture. So in the next problem, for example, what shape is the cross-section if the plane is perpendicular to the base, like this, and passes through the vertex of the pyramid? So I've got to think about, okay, if I slice through the vertex and pass through this way, what is that cross-section going to look like? And it's hard sometimes to visualize that. But if you're thinking hard and you think about, okay, it's going to have one point at the top and it's going to have this point at one side and a point at the other side, it's going to be a triangle cross-section when I cut through that way. And of course, there are other shapes of cross-section that my pentagon pyramid could make depending on where I sliced through to create those cross-sections. Here is a picture of my favorite shape ever. This shape is called a dodecahedron. It is a 3-dimensional shape made up of 12 identical pentagons. So 12 pentagons all stitched up together create what we call a dodecahedron. We're asked, what could I do if I needed to draw a triangle cross-section into this shape? And it's kind of hard to think about with a shape that's as big and as complex as this one. But we can think small. We can say, well, what if I took a little knife or something and I made a slice right here? And I just kind of sliced off this corner. If I sliced off this corner, then what would happen is I would create a little bitty triangle. Let's see if I'm able to draw this. There we go. So if I slice through right there, I'm slicing off this itty bitty triangular piece of the edge or of that corner in the dodecahedron. So thing number 1, we would slice off a vertex. And then the other question is, well, how could I slice through this if I wanted my cross-section to be a pentagon? And if I think about that, if I want my cross-section to be a pentagon, what I'm going to do is I'm going to take my knife and I'm just going to slice a little bit off the top, right? If I just take a knife right through there and I slice, I'm going to get this thin little pentagon cross-section that could help and answer this question. So maybe we'll say that you should slice off a face. Right? So these kinds of questions can be easy or they can be complex depending on how they're worded and what kind of a shape they give you to work with. There's some more in example 4. Here we want to talk about how to draw a cross-section inside of a shape. And actually, a lot of this chapter is going to focus on how do we draw three-dimensional shapes in a two-dimensional space, like on paper, or how do we draw features of those 3D shapes. So the first idea is here we have a tetrahedron. Tetrahedron is the word we use for the smallest possible polyhedron. It only has 4 faces, and each of those faces is an equilateral triangle. This is the least number of faces, edges, and vertices that we can actually have and create a three-dimensional shape. So a tetrahedron is kind of an important shape. Here we want to intersect a plane parallel to the base and draw the cross-section that we would get, right? So if we slice through this parallel to the base, we get a triangle cross-section. And since all of my cut there was parallel to the base, I'm going to draw some lines that are actually literally parallel to the lines of the base of the drawing, right? So I'm lining them up with the lines of the base, and I'll do that for the back part too. And since my lines are parallel to the base and my cut was parallel to the base, this is how I would draw that cross-section, right? Sometimes they're a little wonky. We definitely have issues occasionally getting them drawn correctly, but as long as we understand where they're supposed to be and what they're supposed to stand for, it should be okay. Number 4 says, well, what if I take this same polyhedron and I instead draw the cross-section if I draw through the top perpendicular to the base? And I think I'm going to draw this as if I'm slicing this way. Like I'm slicing a big rectangular object through, so I'm looking at it from the front. And I'm thinking, okay, well, it's going to go through the top, so that's going to be part of the cross-section. And it's going to go through somewhere along this line it's going to hit, right? There's going to be a cut right here and a cut right here. So let me go ahead and draw those in. And then I'm going to connect them together because this ends at the floor level or at the flat part of the base there. And I can color this in and say, all right, well, this is one way it could look if I made my intersection, my cross-section, go straight through the top and be perpendicular to the base. There is a tetrahedron model on your different models that you can look at on Schoology, so you can play around with the tetrahedron if either of these shapes does not really make sense in your brain. Example 5 is, interestingly, the opposite. So in this case, we're not going to start with a three-dimensional figure and cut it to look at the two-dimensional faces. We're going to start with a two-dimensional figure and rotate it or revolve it to create a three-dimensional shape. And for this, you might have to sort of do some visualizing. Imagine that ABC is a triangle made of paper. And it's made of paper and it's taped to a string or a chopstick or a stick right here. And I'm going to take my hands and I'm going to spin this stick really fast. And that's going to cause this sheet of paper that's triangle shaped to spin really fast around the stick. What I'm going to create is called a solid of revolution, where I have these edges, these vertices are going to create a path around this stick or this string in three-dimensional space. And that three-dimensional space is going to show a three-dimensional shape. So for 5A, we're saying if I use line BD, that's where the stick is, and I'm rotating around the stick, what kind of shape am I going to get? I'm going to end up with a cone because these two bottom corners, they're going to rotate around and create a circle. And I'm going to have these straight line sides that go up from my circle that all intersect at a top point. So that'll be a cone. The other question I have here is B, what three-dimensional figure is formed by rotating triangle ABC around BC? So then my stick is going to move, or my string is going to move. This is going to be my string now. And this string, if I spin it, I'm spinning it this way, so I'm creating a shape that's spinning around like this. That's a weird shape. It's kind of hard to say what shape that would be because we don't have a good name for it. Our book is calling it a double cone. So I'm thinking when I revolve this, I am creating a circle like this using A. And then there's going to be straight line sides that connect to point C and connect to point B up here. So it's kind of like a cone on the top and a cone on the bottom, or what they say, a double cone. Both cross sections and solids of revolution can be really tricky if you have trouble visualizing 3D stuff. So please make sure you use the resources available to you on Schoology to really kind of play around with it, rotate things, and develop that skill set. It's something that really does need to be developed as we go through this chapter, doing more with three-dimensional shapes. All right, hopefully that helps you out and you can work on the assignment for this section. Thank you.